Welcome, dear students. Now we are again back with a new lecture on the series of our lecture on novel drug systems. Myself, Dr. Ajay Semalti from HNB Gadwal University, again welcome you in the series of lectures on novel drug systems. So today we are going to deal with dissolution and biopharmaceutical classification system, that is called BCS. We have discussed the various aspects of Ndds. In the last lecture, specifically, we discussed the interplay of solubility, pH and pK with respect to the formulation. Now, in continuation of our previous lecture, I would like to elaborate the concept of dissolution and put together solubility, dissolution, permeability. We will study the BCS and its importance in the formulation of a dosage form or the delivery system. So let's start our discussion. After completing this lecture, you will be able to understand the concept of dissolution theories, factors affecting dissolution. You will be able to run the permeability studies. You will be able to understand the basis of biopharmaceutical classification system and also its importance. We will cover this lecture under the heads dissolution goals, basic concepts, its theories, dissolution apparatus, factors affecting dissolution, permeability concept, determining permeability, diffusion cells, BCS, biopharmaceutical classification system, its concept, class of drugs, examples, and application of biopharmaceutical classification system, that is BCS. Now, what is dissolution? As we've discussed earlier also, that what is dissolution? Briefly, we discussed in solubility part that it's a kind of solubility with a function of time. So let's define it. That dissolution is defined as the process by which a known amount of drug substance goes into solution per unit of time under standardized conditions. Okay. So please remember this definition. Let's take another definition, that dissolution is defined as the process by which a known amount of drug substance, that we have gone through this definition. Now it is used for characterizing the biopharmaceutical quality of a product at different stages in its life cycle. We need the dissolution for choosing between different alternative formulation for further development. It's a kind of benchmarking the or quality. It's a perfect quality control test. Okay. Taking the another definition, that dissolution testing is an official test recommended by all pharmacopoeia for evaluating drug release of solid and semi-solid dosage forms. Now, what are the goals of dissolution study, dissolution testing? We need to perform the dissolution for the prediction of in vivo performance, to assess the lot-to-lot quality of drug product, and to guide development of new formulation. Now, if we want to elaborate the first point, that prediction of in vivo performance, why prediction? It is not possible practically to go each and every time for the in vivo studies. We perform a set of condition of in vitro and then perform the in vivo of the same formulation and try to correlate them. That is called IVIVC, in vitro in vivo correlation. When this correlation is set up, we need not to go for again and again to the in vivo study, because it is not only time consuming, several regulations are there, and cost factor is there. So what we will do, that we will predict on the basis of in vitro release, we will predict the in vivo performance. So that's why the dissolution is the most important factor for when we are asking about the correlation. We completely rely upon on the dissolution profile, in vitro dissolution profile. And also, we cannot go for every lot of your production for in vivo studies. So we can assess the lot to lot quality from one lot to another lot whether they are consistent in performance in release, we will do the dissolution and it will indicate their consistency. Okay, and specifically for the new formulation, it is required. For the prediction of in vivo performance, as we have said that again, to ascertain the need of in vivo comparative bioavailability and bioequivalence studies. So we need these dissolution studies for bioavailability and bioequivalence studies, whether the two products which are pharmaceutically equivalent are bioequivalent or not. Okay, being pharmaceutically equivalent may be another factor, but what is required is that they must be bioequivalent. Their efficiency, their release, their biological properties, you can say their the release properties must be equivalent. So a mandatory requirement for regulatory approval, it is dissolution is, as we know, that is the official test. So it's a regulatory requirement. Without this, you cannot you cannot get the green signal for going into the market. Okay. To assess quality in terms of stability, expiration date, and optimizing the product, we need the dissolution. That's why we do perform the dissolution. Now, dissolution is basically the drug going into the GIT, and it is a step before the permeability. As we can see here, this is the step of dissolution. Drug is going into that GIT or the biological fluid and trying to enter into trying to pass across the biological membrane, followed by the dissolution. So it's a two-step process basically. Step 1, molecules are released from dosage form to media, creating a saturated layer or stagnant layer adjacent to the solid surface, and the drug diffusion as per the concentration gradient occurs. So we can say that it's a two-step process. The rate of drug dissolution. What is the basic concept? The rate of drug dissolution at a specific time is expressed by modified Noyes-Whitney's equation. dx by dt is equal to adk upon h into cs minus xd upon v, where dx upon dt is the dissolution rate, a is the surface area of the particle available for dissolution. It is called the effective surface area. Please do remember. And it is the surface area available for dissolution. D is the diffusion rate constant. K is the oil water partition coefficient. H is the thickness of the stagnant layer surrounding the particles. Cs is the saturation solubility of the drug, and xd is the amount dissolved of drug at time t, and V is the volume of dissolution media. So remember this definition, this equation. Whenever you are explaining dissolution, it is at most necessary that this equation must be there in your answer. Okay. Let's see, on the basis of this equation, you can enumerate the factors which are affecting the dissolution, like number 1, surface area of drug A, which is dependent on the physicochemical properties like particle size, wettability, and the physiological properties like surfactant in gastric juice and bile may affect this effective surface area. Diffusion coefficient of the drug D is dependent on molecule size. Viscosity of and the viscosity of luminal content is affects this thing. Stagnant layer thickness. Okay, the motility pattern and flow rate can modulate the stagnant layer thickness, while the solubility, saturation solubility, we are talking about that hydrophilicity, crystal structure, solubilization, they affect this solubility. pH, buffer capacity, bile and food compositions, they affect this solubility. Amount of drug release, drug already dissolved, xd, is governed by the permeability factor, and the volume of solvent available, V, is basically affected by the physicochemical properties of like secretion and co-administered fluids. So by these factors, physicochemical and physiological properties factors, these factors of dissolution are governed. Now, if you want to study the dissolution, there are three major theories of the dissolution. Number 1, diffusion layer model, that is called film theory also. Penetration of or surface renewal theory, that is Dankworth model, interfacial barrier model, that is double barrier mechanism or limited solution theory. You might have studied uh, in your biopharmaceutics text, though we will be covering a little bit of these theories. Taking the first theory, diffusion layer theory, as the name suggests, it is a diffusion layer theory. A layer is there formed, which is diffused there. So step one is formation of a saturated stagnant layer around the drug particle in solution. That is a rapid step. Then it is followed by the drug diffusion from high to low concentration. Higher concentration is around it, around this core. So drug diffusion from high to lower concentration. It is the slow and rate limiting step. So step 2 is the rate limiting step, which is actually governing the overall release. Okay, overall dissolution profile. As you can see in this figure, clearly shown that solid drug particle is there in and around it a stagnant layer is formed, which is having a thickness of H. Okay, the saturation solubility CS is indicated here, and the drug is slowly diffusing from this stagnant layer to the bulk of the GI fluid, and then it is going for the permeation. So diffusion layer theory can be explained by this diagram. You must draw this diagram whenever you are answering the theories of dissolution. Okay, moving to the next theory, surface renewal theory. So surface renewal theory, it is continually exposed to fresh dissolution medium. Numerous eddies or packets are there in the agitating medium. What happens, that solute diffuses into the packets and is carried to the bulk medium, as we will see in this diagram, that unlike previous theory, no stagnant film layer is there due to turbulence or constant surface renewal. So surface renewal is the prime factor here. Let's see in this figure that solid drug particles are there and drug is going to those in those packets, solvent packets, and then it is being carried to the bulk. Okay? And the surface renewal is happening again and again. Moving to the interfacial barrier model, it is also called limited solution theory. A crystal undergoes dissolution through an interfacial process in the dissolving medium, and the true surface area of the crystal must be considered for this, for explaining this, and each surface provides a different contribution to the dissolution process. It can be very easily understood with this figure that how interfacial barrier model can be explained in this diagram. So please mention it whenever you are explaining it, these theories. The figures must be there supported with your other things. Now moving to the dissolution apparatus. Uh, Actually, dissolution is an apparatus which reasonably mimics the physiological conditions available in the GIT. Jar, that jar mimics the GIT, because that's why it is its bottom is hemispherical, just which is trying to, as you can see in this diagram also, the jars are hemispherical, and actually it has been tried, the efforts has been focused to mimic the GI environment, because the stomach and the intestine, they are basically hemispherical in nature. Okay, they are corners. Like if you see the stomach is the bottom part is hemispherical. We are trying to mimic that environment. Secondly, is volume like gastric media, like 900 to 1000 ml is there, because in gastric media the same amount is there. So the capacity is 900 to 1000 ml of the jar of that dissolution apparatus. Temperature is maintained by the maintained at body temperature by the heater. Uh, Agitation is given by the paddle or basket to mimic the gastric motility. As you can see in this diagram also, however, we have it has been removed right now because in the standby condition. As in upper part, you can see these are the hooks. These are the parts from where the paddle or basket is hanged, and the agitation is given through this shaft, which is driven by the motor. Uh, it may be single station or multi-station. Right now, which you are seeing is it is a 8-station dissolution apparatus. So official dissolution test apparatus IP, that is pedal type 1, and basket type 2. Remember that in IP type 1 is pedal type, while in USP type 1 is basket type. It is very important. Many times in Viva and in examination this is asked. It's a tricky thing, simple thing, not much you can say, but it indicates your attention to the topic, that how much tuned you are with the dissolution apparatus. So what you have to do, that in paddle, which is as the name suggests, is the paddle hanging on the jar, and in the basket is a mesh of a basket is there, which is of mesh of a certain height, length, mesh size. Each and everything is specified. So as you can see in this diagram, you must have the idea of the measurements, specifications of each and everything when you are reproducing it, when you are answering it in your answer book. In the USP and IP, the specifications are same, but just the name is different, as we have discussed. So just remember each and every specifications perfectly. Okay. So we have discussed about the IP. Let me tell you something about the dissolution test apparatus USP. There are seven types of dissolution apparatus are there. Okay. Uh, First is rotating basket. As we are told, is type 1 is basket here. Type 2 is paddle. Type 3 is reciprocating cylinder. Type 4 flow through cell. Type 5 paddle over disc. Type 6 cylinder. Type 7 reciprocating holder. So first two, basket and paddle, are for oral immediate release and modified release. IR stands for immediate release, MR stands for modified release. IR and MR, and reciprocating cylinder is meant for modified release, and flow through cell is also for the modified release dosage form. However, for the Ndds like transdermal delivery system, paddle over disc and cylinders are there, and also the reciprocating holders. uh, See that what is the paddle over disc, which is a very common type of dissolution apparatus. What we do here, in simply the jar, you can prepare a dish can be inserted, which is up relatively at the up slightly above from the bottom of that hemispherical jar, and you can affix that transfer patch onto that disc, and paddle can be hanged. So paddle over that disc in this jar. So it's simple. You can design it in your own dissolution apparatus. Okay, so what you have to do, due to limitations of the time and topics to be covered, with the interest of time, I'm skipping the diagram of each and every type of these dissolution apparatus. What you have to do, go to USP or go to the internet and search these all the types of USP dissolution apparatus, and try to redraw them and learn them. Okay. Dissolution apparatus factors. Now, what are the factors which are governing the release? Type of apparatus, dissolution medium, agitation, and temperature. These are the four major factors. Okay. In dissolution medium, what we are trying actually? Medium is our effort to reasonably mimic the physiological conditions like volume, pH, etc. To stimulate the intestinal condition, we can have the simulated intestinal fluid. A dissolution medium of pH 6.8 should be employed for this SIF. For SGF, simulated gastric fluid, a dissolution medium of pH 1.2 should be employed without enzymes or with enzymes. To achieve sink condition, if drug is less soluble, co-solvent or surfactants are used. So it is not always that we are trying completely to mimic the environment of the GIT or the other thing. For bioequivalence studies, solvents which yields similar dissolution profile is used rather than the solvent mimicking the physiological condition. You might be seeing that sometimes complete dissolution is done in the methanol, complete in acetonitrile or the mixture of methanol acetonitrile. You may ask that that it is not the natural dissolution fluid. Why we are using it? Actually, our aim is to establish the bioequivalence, that what is the standard drug is showing that dissolution profile, we want to mimic it. Okay, so in the same dissolution media, your standard drug, okay, for which you want to make a copy, what you will do, that same media, the response would be same. So we will try to maintain the equivalence. So we will take a particular dissolution media which can show the similar dissolution profile for the standard drug as well as your own copy drug which you have prepared. So this is the bioequivalence study. So in bioequivalence study, we don't go for solvent mimicking the physiological condition. We just go for the media which can show the similar profile for standard as well as your own copy drug which you are trying to develop. So remember this thing, and you must have a clear-cut idea in your mind. Now, International Pharmaceutical Federation (FIP) recommends a dissolution media for dissolution media 0.1 SCL, buffer solution pH 4.5, stimulated intestinal fluid without pancreatin pH 7.5, and 0.05 m phosphate buffer solution of pH 5.8 to 8. So these are the 4 recommended dissolution media by FIP. Uh, what is called rapidly dissolving in dissolution? An IR product, an IR drug product is characterized as a rapid dissolving when no less than 85% of the labeled amount of the drug substance dissolves within 30 minutes using USP apparatus type 1 at 100 rpm or USP apparatus type 2 at 50 rpm in a volume of 900 ml or less of each of the recommended media. And you know that the FIP recommends the 4 dissolution media. So what I mean to say by this, that if I am saying the rapidly dissolving, it is not an abstract idea that it is rapid. How much rapidly dissolving? So each and every condition is specified, that to which thing, to which IR product you will classify as a rapid dissolving. So it should be dissolution must be no less than 85% in within 30 minutes in apparatus type 1 100 rpm or type 2 50 rpm with a volume of 900 ml recommended media. Okay, or you will have to learn these specifications when we are uh, trying to recollect the idea that what is rapidly dissolving. Okay, now agitation. Agitation actually mimics the gastric motility. The agitation, whenever we are taking a dosage form, a gastric motility starts. Okay, so if we want to mimic the gastric motility, we will have to agitate that media. So mild agitation conditions should be maintained during the dissolution testing to allow the maximum discriminating power. So agitating conditions are of that capacity that they can discriminate between two dosage forms. Okay, for their performance, agitation is done to detect the products with poor in vivo performance. You can have the RPM 50 from 50 to 100, 50, 75, 100. You may see in monographs, in some monographs, in most probably in the SR dosage form or modified rate dosage form, it is that agitation is average 50, or in the IR product is in general it is 100, and in between in some cases 75 is there. Actually, this selection of agitation is done on the basis of the discriminating power. We will choose a agitation speed which will have the maximum discriminating power in between the performance of two products, of similar products. So what happens, that agitation must have uh, a capacity to discriminate between two products. Okay, for average for SR, why we are taking in lower agitation, because it is moving. We want to see the performance from gastric region where high mortality is there, and in the when you are going to the distal end of the GIT, the lower mortality rate is there. So we will have a average lower. The average will be taken as the lower one as of the highest one. So in gastric region it may be 100 rpm, but we will take it 50 rpm for as an on an average agitation speed for studying the dissolution profile of a oral controlled drug delivery system. So generally we go for the RPM speed mentioned in the monograph until we are developing a completely new Ndds or completely new dosage form. Temperature is the again the factor that minimum what we do, that we mimic the body temperature at 37 plus minus 1 degree Celsius. Temperature of apparatus must be maintained before the beginning of test. You cannot do like that. Some students, specifically the undergraduate UG students, what they do, they start in the however in these all the multi-station dissolution apparatus, it doesn't start until it maintains the temperature of 37 degrees Celsius. However, it was possible in case of single stage. It is possible in case of single stage where there is no smart system. So you can start your dissolution immediately after opening it. So what you have to do, whether your system is not you having this system or not, you just ensure that whether you are uh, the apparatus temperature has reached to the body temperature, the 37 degree or not. Okay, even in some cases, in some due to the heating failure, due to the thermostat failure, the temperature may not be reaching. So you will have to ensure even in the smart systems. So increase or decrease in temperature may affect the solubility and the dissolution. So that's why they are very important. If you and the harmonization, the reproducibility of result will not be ensured if you will not ensure the exact temperature maintained for each and every test. Now, permeability, as we see that the GIT drug goes, that transfer of passing across the biological membrane needs the permeability properties. As we have already studied that drug permeation from is is follows only the dissolution profile. Say drug is going into the GIT. Let's see. Yeah, it's going. Then again it is passing the membrane and then getting absorbed. Isn't it? So this for this permeability is a rate limiting factor, or you can say permeability is the you can rate limit. Dissolution is again a rate limiting factor, but permeability may be a rate limiting factor for the poorly permeable drugs. Okay. Now it is how permeability is predicted. Permeability is predicted by the partition coefficient. It depends on chemical nature of the drug, depends on molecular weight of the drug and microenvironment of the drug. That's the three major. However, there may be some other factors, but they are the three prime factors. A drug substance, now how to which substance you will tell highly permeable? As we discussed, rapidly dissolving. What is rapidly dissolving? What are the standard conditions? A highly permeable drug. A drug substance is considered highly permeable when the extent of intestinal absorption is determined to be 85% or higher. In before 2016, this cutoff criteria was 90%, but it has been relaxed to 85% in the recent guidelines. So permeability is assessed by the in vitro diffusion cells. So for permeability we need the in vitro diffusion cells. And let's see some of the diffusion cells. That what these in vitro diffusion cells are smaller in size. They are having the two compartment, donor and receptor compartment, and in between them a semi-permeable membrane. It may be a human cadaver skin, rat intestinal skin. It can be mounted in between these two compartments. The media in the receptor compartment is agitated on a magnetic stirrer, and samples are removed at different time intervals by replacing same amount of pre-warmed media each time. As you can see, the French diffusion cell and the Case-rich diffusion cell. Actually, the diffusion cells are of two types: vertical dissolution apparatus and horizontal diffusion apparatus. Okay. In the vertical diffusion apparatus, there are the two major types are French diffusion cells, Case-rich chain cell, Casey cell, and another is Java-Lordi cells are there. Apart from there, horizontal cells are all there. The Valia chain cell, VC cell, and Ghanman chain cell, GC cell. Please, again, I would request you to go through your text, search the diagram of these apparatus and try to understand them. I will let you know about I will like to give you a live demo. Let's see. This is the a diffusion cell which we have designed for our lab only. Actually, you can make any diffusion cell as any diffusion cell. There are no standard conditions actually. Until you are having a good, you are mimicking the hydrodynamic and the thermodynamic condition, you can make any design. Okay, you can see that this is the sampling port. Outer jacket is there. Okay, the water inlet or water outlet is there. Water inlet is there. Water outlet is here, and you can see, if you see, I will focus to the camera, that inside there is the receptor compartment. Okay, the receptor compartment media is there, and the above part, above which you will put a membrane here. You will put a membrane here. Okay, and membrane, then the donor compartment comes. This is a donor compartment. Okay, as you can see, the donor compartment. This is a donor compartment. Donor compartment can be clipped with the help of some clips, and when these are in place, the in between them we have kept in place, with the help of clips we can clip them together. As you can see, these are the clips, and the clips can be hanged at the receptor compartment, donor compartment are packed with this thing. So, and then the entire assembly, the receptor compartment filled with the PS 7.4 buffer, and the outer jacket is giving the water is being flown to control the temperature, and this entire assembly, and in the inside you can put a smaller bead there, which will provide the agitation on when it is kept on the that magnetic stirrer. And you will take the samples from here. You will take the samples from this side time to time, and you will replace this same amount of pre-warmed receptor fluid to maintain this fluid. Okay, to maintain that sink conditions, you can say. So this is about and we have designed it in a glass blowing lab, so you can give thing. However, the commercial products are always there, they are quite expensive. So for the laboratory purpose, you can design yourself. Okay, so this was all about, so dear students, this was all about the diffusion cells. So what I have told you, that there are the vertical diffusion cells and horizontal diffusion cells. Okay, these two types of cells, different diffusion cells, you can design yourself also in the laboratory, provided you are maintaining the hydrodynamic and thermodynamic condition. Any apparatus can be modified into the diffusion cell. Okay. However, the artificial membrane also comes, nitrocellulose membrane and other kind of membranes, cellular membranes are there, which are available as commercial membranes are available with certain pore size depending on your requirement, which can be placed in between the donor and receptor compartment. Now moving to the BCS classification. It is a drug development tool which was proposed by the Amidon in 1995. It is based on the aqueous solubility and intestinal permeability. Okay. Now, why we need this kind of classification? Actually, based on the aqueous solubility and intestinal permeability, BCS classification, on the basis of dissolution, solubility and intestinal permeability, the rate and extent of drug absorption from solid oral dose form is governed. So these three factors govern the rate and extent of drug release. So it was thought that why not to create a system which can govern the which can classify the drugs in some classes on the basis of these three things. Class 1 drug, class 2 drug, class 3 and class 4. BCS has the 4 classes. Class 1 drugs, high solubility, high permeability. Class 2 drugs, low solubility, high permeability. Class 3 drugs, high solubility, low permeability. And class 4 drugs, low solubility, low permeability. Okay, remember this thing: high, high, low, and low, low. Don't mention them in wrong way. Okay, it is called 4-box amidon model. There are 4 boxes: class 1, class 2, class 3 and class 4. Okay, as we mentioned, the class 1 as a green one and class 4 as a red one. Okay, and class 2 is the yellow one. You can say that is okay. Class 1 and class 3 are okay because both are having the high solubility, but problematic factor start from the class 2. However, in some cases, class 3 is also a problematic factor, but class 4 is the most problematic classes of drug. It this slide shows the top 200 marketed drug in USA by BCS. By BCS, you say that BCS class 1 drugs constitute 31% of the drug, while the BCS class 2 drugs are having 30%, by BCS class 3 23% drugs, BCS class 4 6% of drugs. While NC prevalence, that new chemical entities are there, that the prevalence by BCS, that BCS class 2, whatever the new chemical entities are coming into the market, BCS class 2 drugs are 70%. Means 70% of drugs which are coming new are actually under the BCS class 2, while BCS class 4 drugs are 20% there. Okay, only 5% are in class 1 drugs. So it is to be kept in mind that we have to make our efforts in improving the solubility part. So that's why the solubility improvement is needed, which we discussed also in the solubility part, that we must know about the various strategies for going for the solubility improvement. Okay, so this shows that depending on the classification of BCS, we must focus our efforts on the certain classes of drugs. Okay, you should not waste your efforts in the BCS class 1. That rational, we are again and again emphasizing the rationality of developing the Ndds is very much important. Okay, students may do some mistake, but they must have in their mind that rationality is the prime factor. Solubility, in the BCS, solubility is based on the highest dose strength in an immediate release product. In the BCS, solubility is based on the highest dose strength in an immediate release product. A drug substance is considered highly soluble. When it will be called highly soluble? When the highest strength is soluble in 250 ml or less of aqueous media over the pH range of 1 to 6.8. Okay. So from pH 1 to 6.8, it should be soluble. Okay. Then it will be called highly soluble. And the volume, it should be soluble in the 250 ml or less. Okay. In the similar manner, we will define the permeability. It is based on directly on the extent of intestinal absorption in vivo in human, or indirectly on the in vivo drug transfer across the human intestinal membrane. A drug substance is considered highly permeable when the drug extent of intestinal absorption is determined to be 85% or higher. This must be kept in mind. Okay, 85% or higher is that criteria by which we say that this drug is highly permeable, because on the basis of high solubility, high permeability we are asking. So this model is depending on these definitions, solubility and permeability. What is highly soluble, what is highly permeable, it must be known to each of you. You can't skip that these definition when you are discussing the BCS. You must mention what is highly soluble, what is highly permeable. Then you will design that on the basis of solubility and permeability, these 4-box amidon model can be given. So let me give you some examples of these BCS classes. Say for example, in class 1, rofecoxib, paracetamol, propranolol, metoprolol. In class 2, nimesulide, nifedipine, phenytoin, digoxin. In class 3, acyclovir, atenolol, ranitidine, diphenhydramine. And in class 4, cyclosporin A, furosemide and amphotericin B. What happened that a few years back, before 2016, the high permeability range, as I discussed earlier also, that it was 90%. That criteria was relaxed to 85%. So many of drugs were being classed in class 2. So they were shifted from class 2 to class 1 on the basis of the permeability, because they were having the permeability in between 85 to 90. So previously they were in class 2, but when the criteria was relaxed, many of the drugs were shifted from class 2 to the class 1 drugs. Okay, so there are so many drugs. So that's why even in the class 2, you will find in some text the class 2 is subdivided in two subclasses, class 2A and class 2B. So you can go through that how they are being classified in class 2A and class 2B. See, if you want to go in detail, there are very wonderful texts by Dressman in dissolution testing. I just recommend that text. Please go through. It is a wonderful text, specifically the persons who are aiming for going into the pharma industry. Now, let me tell you something about the BCS applications. We require the BCS for in vitro dissolution profiles and in vivo biologic correlations. IVC, in vitro in vivo correlation. For this, BCS classification is utmost desire. I'm saying that this is the drug which shows this kind of in vitro profile, okay, and this kind of in vivo profile. So whatever you are preparing batch to batch, again further batches are there. So if you will assess the in vitro release, it because the correlation is good, so we can predict the in vivo in with a good confidence. With statistically significant confidence, we can say that yes, our drug is bioequivalent to that standard drug, and we can correlate this IVIVC. But provided the IVIVC correlation is good, by just going through the in vitro release profile or dissolution, we can predict the in vivo. Okay. For developing the in vitro dissolution specs, we need the BCS classification. For many new drugs, for many new Ndds, when you are developing, you have to give the BCS specs. Okay, the in vitro dissolution specs you need, you want to give. So for that, BCS is required for developing a strategy for improving the bioavailability of new chemical entity. Now, you want to improve the biological the availability. For planning that strategy, you must go ahead with the BCS. You must classify the drug into the particular class, and then you will plan that strategy. You will classify it, you will find that particular class, and then you will plan the strategy, because for every class that strategy is different. Okay. For predicting the drug bioavailability, as we have mentioned that solubility or permeability rate limited drugs, the BCS, depending on the BCS class, we can predict the bioavailability. So it is utmost important that you must know the BCS class of your drug under investigation. If you are doing your project and you don't know the drug class, the BCS class of your drug which you are using, believe me, it's a crime. Yeah. Why? Because it is the basis of rationality. It is the basis of rational. Why you are preparing this Ndds? Why you are using? Everything is based on that thing. You must have the good rational, and that classification, BCS classification itself a good rational. If you say that, sir, I have a drug, this say for example paracetamol drug, and a drug which is very highly soluble, or you are preparing, until unless you say that, sir, I have used this as a model drug, the rationality must be there. For a BCS class 2 drug, you are improving the solubility, perfectly okay. If you are improving the solubility of BCS class 1 drug, rationality is a problem there in that case. So you must be very cautious, and it should be the prime request to identify the BCS class of a drug or a new drug for a new dosage form for developing the new novel drug system. So these are some references, as I have mentioned that some of the group and this theory of dissolution and theoretical concepts for the release of a drug from a dosage form, dissolution, bioavailability and bioequivalence by the Abdu. It's a classic test. I liked it very much. And Dressman's and Karmer text, pharmaceutical dissolution testing, is again a wonderful text for for referring for the dissolution testing. You must study these texts for if you want to go for the further readings for the dissolution and the BCS classes. Okay. Now let me summarize this aspect for you, that how dissolution, which is a quality control test, helps you out. Dissolution is required for predicting the drug release, batch to batch consistency, in vivo performance, bioequivalence and Utmost important thing is it's a regulatory requirement. Dissolution is an official test for almost each and every dosage form or delivery system. You cannot skip. Solubility, dissolution, and permeability, they govern the absorption of drug after the oral ingestion. As far as the dissolution is concerned, dissolution can be explained with the help of three major theories, film theory, then your limited solution theory, and your Dankworth's model. So these three theories can be described by equations like modified noise witness equation defines the diffusion layer theory, diffusion layer model. So you must know the factors which are affecting the dissolution, how the dissolution can be improved, because unless you know the factors which are affecting the dissolution, you cannot work upon those particular points that what should be focused. Okay. Now, on the basis as we discussed the solubility, resolution, and permeability, they are the three factors. You must know what is highly soluble, what is highly permeable. Okay, when you are discussing the BCS, that amidon four box model, you must know what is highly soluble, what is highly permeable. Okay, with the definition. Then give those model, that four box model: highly soluble, high permeable, class 1; low solubility, high permeability, class 2; high solubility, low permeability, class 3; and low solubility, low permeability, class 4. So in general, these are the punch points you are taking away with this lecture, that you must ascertain a drug, you must ensure that you know the BCS class of the drug, and your efforts should be focused in identifying the BCS class of a drug, because this is the basic requirement for developing any dosage form, and all your efforts and all your planning depends on this BCS class. So besides this, please don't forget the diffusion apparatus. Diffusion apparatus are very important. Horizontal and vertical diffusion apparatus are there. We have discussed a few, we have given the live demo of the vertical dissolution apparatus. We have shown you a French diffusion cell which we have designed ourselves, and you must go through the diagram of vertical dissolution apparatus and horizontal one. Okay, just go through the text, redraw them, practice them, and they are certainly going to be asked in your question whenever either they will be asked with the BCS or dissolution, or they will be asked in the transdermal drug delivery system. So certainly they are going to come in almost in every exam, specifically for M.Pharm exam and also for the Ndds paper of the B.Pharm 8th semester. It is asked. So please do practice, and for further studies go through the text which I have recommended. Thank you for being with us. It has been a wonderful experience to let you know about the things and to easing out the problems which you might face in answering these kind of questions for your exam point of view. So thanks for being with us. I'll be coming up with the new lectures on the new topics on the Novodex system in coming days. Thank you for being with us. Happy learning.